Talked about willingness to pay versus willingness to accept compensation, but I didn't get to benefit transfer. Typically in environmental evaluation, we are concerned with benefit transfer because primary evaluation studies are difficult and expensive. So what we do is we take an estimate of the value of something from one place, from one issue, from one study, and then somehow transfer it to another place or another time or another issue. Climate change, the reason for doing this is different. Climate change is something from the future. We cannot travel there, estimate things and travel back and report on what we found. So we have to rely on benefit transfer. In two ways. One is over time. We value things for today and then have to derive what would values be for the future. And the other extrapolation is that we estimate these things in the context of something and then apply them to a context of climate change. And we have to assume that the two contexts and the two causes do not affect our ability to estimate or does not affect our confidence in estimating these values. There is a lot of experience with benefit transfer, and that experience is not very encouraging. What studies have found, and I'll show you examples in a minute, is that the valuation of environmental goods and services turn out to be highly context specific. And that we're not very good at forecasting how this context affects the values. So here is an example from a study by Marianne Sanderson. And the context is the value of forest recreation services in Denmark. And it's all, so Denmark is a small country, right? Relatively homogeneous country, so that makes it easy. These are revealed preference studies, so that also makes it easy in the sense that you don't have all the biases that come with stated preferences. And the dots that you're looking at here are the, I believe, 56 forests that there are in Denmark. As I said, it's a small country. They don't have too many trees, apparently. And the context that she tried to do this is, as I said, a revealed preference study where she first estimated the value of these forests in the early 80s, and then she repeated the study in the early 2000s, 1980s obviously, and then she predicted the value for the year 2000 from the studies in the 1980s. And the question is, did we get the prediction right? And the good thing about this study is that she also had the data for the year 2000, so she could check her forecast based on the data from 1980. There's two transfer methods used here, one a naive method, just assume that the value hasn't changed, and that is what you see happening here in a second was to make the prediction of the value of the forest a function of the density of the trees and the type of the trees and the sort of people who would go there and how they would get there, and then sort of like plug in how things had changed in the 20 years. For instance, a massive increase in visits by car relative to other forms of transport. Put all those things in, and then this predictions result. And what you see, and that is the most important thing, is that only in a minority of cases did the prediction come within 100% of. Yeah, this is the error of margin, within 100% of the value that was estimated in the year 2000, right? So not 1980 forecast to what would the value be in the year 2000, no, what did we observe in the year 2000. And in a few cases, it was off by a factor 4. And this is a simple exercise, right? This is Denmark, a country that doesn't change rapidly, a country that is small and homogeneous, and the forecast was only over a 20-year period. So you can imagine what the forecast errors would be if we go for something more complicated. I should press here. Similar exercise here. People, again, this is mostly recreation, so mostly reveal preferences. What if we measure the value of sport fishing in one site and then go to a site a little bit further in the US, error margins of 5 to 40%, 5 to 50%, water quality improvements, and so on and so forth. And what you see is that the error margin is rarely very low. We have a couple of cases where we actually could get within 1%, but sometimes they go up to 500% or so. So a factor of 5 difference between the measured value and the predicted value to the best of people's ability. And these are naive transfers, and these are not so naive transfers, but you see that it doesn't make a big difference, and in some cases naive estimates are actually a little bit better. So this introduces an enormous amount of uncertainty into what we know about the impacts of climate change. But we have to do this because we can't travel to the year 2050 and wonder how much value would people attach to a loss in the quality of sport fishing. No, we have to measure that today and then project it into the future. That is an important thing to keep in mind. So, to what I was supposed to start with this afternoon. I showed you this picture about the various projections of what the future of climate may be. I talked about the alternative reasons for concern, and that some people who care about unique unique systems such as atolls or species such as butterflies, you have very good reason to be concerned, deeply concerned about climate change. If you only care about the West Antarctica ice sheet, then perhaps climate change is not your priority. And I'm not going to tell you which you should be adhering to, right? This is your choice. Do I place more emphasis on these risks or more emphasis on these risks? That's your business, not mine. What I'm going to talk about next are the two reasons for concern in the middle. That is, what would happen to global aggregate welfare. And next week I'm going to turn to the distribution of welfare. So if we focus just on what would happen to the well-being of the average person on the planet, then this picture emerges. So what are we looking at? On the horizontal axis, we're looking at scenarios of climate change. And they're measured by the increase in the global mean surface air temperature since pre-industrial times. So zero change has a zero impact, right? And then on this axis, we're looking at the welfare equivalent income change. It's a bit of a mouthful. Essentially, the way to read this graph is that if the world would warm by 2.5 degrees, then the average person on the planet would feel as if she had lost 1.1% of her income. And 1.1 is the average of the blue dots that you see at 2.5. So that's how to read it, right? If you would lose some of your income, you would feel bad. So you can express that as a welfare equivalent. And if you if climate would change, that would also on net make us feel bad, and we can then equivalize the two as to the welfare loss. And that is what people have done here. Where do these numbers come from? The method used most is the so-called enumerative method, where essentially people did roughly what I did this morning. They went through the literature on all the different impacts of climate change, came up with the best estimate of how would the yields of wheat change and rice and maize, how much would energy demand change, how much would health change, how much land would be washed away by the sea, and so on and so forth. A long list of impacts in their physical units or their natural units. Then they would use the valuation methods that we also talked about briefly this morning to estimate the value or the price of those things that are not traded on markets, and things that are traded on markets. It's much easier, right? For instance, if you're concerned about the cost of dike building, then you should call up one of the commercial companies that builds dikes and say how much would it cost to raise a kilometer of dike by 1 meter, and they can tell you 6 million euros, 6 million pounds. You have the quantities, we have the prices, you multiply the two, you add them up. Right? That's what people have done. And that's what actually most of the literature does. It's a bit of a silly method, right? Because if you have large shocks in quantities, you would expect also that the price would not stay constant, right? You would at least impose a partial equilibrium model. That's not what people have done. Or you could imagine that if the impacts in one sector are large, then it would also affect the rest of the economy. So what some people have done, but this is much rarer, is to do the same exercise, quantify the impacts in their physical units, then stick them into a model of the whole economy, including all the interactions between sectors as well as international trade and investment and what have you. So-called computable general equilibrium model, and then estimate the welfare change that comes out of it. That's what a few people have done. Yet other people have used statistical methods or enumerative methods, where in the first application what people did was run a regression of the value of agricultural lands on climate, assuming with David Ricardo that all the aspects of a piece of land, and if you buy a piece of land, you also buy the climate that comes with that piece of land, The climate would affect productivity of the crops or the suitability of that land for growing particular crops. So in a way, the climate that you buy with a piece of land is capitalized in the price of the land. There is a basic thought. So the estimated relationship between the value of agricultural land and climate over space found a nice stable relationship, or so they claimed, and then assume that this relationship is stable over time. There is a bit of a jump of faith there, right? Relationship over time, relationship over space implicitly takes into account that it's easy to travel through space. Now you can travel in two directions in space, whereas a relationship over time, you can only travel one direction in time, you travel at a constant speed, right? So time travel is a lot more restricted than space travel. Over space, technologies are roughly constant, institutions are roughly constant. This was a study for the US only. Over time, institutions change, technologies change, right? So there's a bit of jump of faith, but that's what people did. Initially, we looked at agricultural land values, consumption patterns, and so on and so forth. A bit later, people also looked at the relationship between self-reported happiness and climate, and used that to derive what are the impacts of climate change. And then finally, there's one study in the graph that I showed, and there's one on the way where people just directly elicited the opinion of experts, asking them, what do you think the impact of climate change would be? The study that is in here dates back to 1994, at which time nobody could really claim to be an expert. I would still have my doubts, but anybody claiming to be a true expert in this group. And these studies then should bring you this picture. So what does this picture tell us? I've given you already a few of his messages. There's 27 blue dots here, and that is the population of studies. This is not a sample. There's a lot of noise about climate change in the media, and a lot of people claiming that climate change is the biggest problem of humankind. Some people are a bit more modest and say it's the biggest environmental problem of humankind. So you would expect if people make such bold claims that there would be a lot of evidence to back them up. But there's only 27 studies, so that's a very thin empirical basis to make any sort of claim. So that's one thing to notice. Going back to the order of magnitude, if you focus on 2.5 degrees of warming, then the welfare loss to the mean person on the planet would be a 1.1 income loss. Now 2.5 degrees of warming is something we would expect over a 50, 70, 80 year period. A 1% change in income is an annual change in income. So to put it perhaps a bit chargedly, a century of climate change is about as bad as losing 1 year of economic growth. That is what these estimates tell you. To tell you more things, I already stressed the weak empirical basis. We go focus on. Let's start elsewhere. Initial warming may actually be beneficial. There's one older estimate that actually looks at cooling and what that would do to welfare, and shows that cooling, or argues that cooling would be bad for us. a little bit of warming may be good for us. And the reasons for that are CO2 fertilization, it makes plants grow faster and more drought tolerant, reduction in energy use in winter, which is a clear benefit, as well as a reduction in cold-related diseases, which is another clear and large benefit. So initial warming may be good for us, but then as it gets warmer and warmer and warmer and warmer, things turn negative. These initial benefits are no reason for subsidizing coal. There are no ground for subsidizing greenhouse gas emissions. Why is that? Because of the slow workings of the climate system, the slow workings of the energy system that drive the climate system to a degree, and the slow workings of the political system. And all of that means that this initial warming, already actually here already, the initial warming is in the past, and then further warming is basically sunk. Regardless of what we do, because of the momentum in the ocean, we will get another degree of warming on top of the 0.8 that we've already had. So that brings us here. If you then put in constraints about that you can't just turn around our energy system, let alone that you can convince politicians that that is what they want to do, if you sort of start adding in constraints about the turnover of the capital stock and the slowness of political change, then it's actually very hard to imagine that we can avoid 2 degrees of warming, 2.5, maybe even 3 degrees of warming. Whereas if you believe the red curve, you do not necessarily have to, but if you believe the red curve, we should stop warming at around 1.2, 1.3 degrees. And that is the optimum point, and if we could choose our climate, we would stop there, and anything beyond that is a net negative, right? The incremental impacts become negative, and you should care about the incremental impact rather than the totals. So you would want to stop here. There's no way we will stop here. You will end up here somewhere, and from the point where we can actually influence the climate, the incremental impacts are negative. So we should be, if the shape of this curve is correct, we should be taxing greenhouse gas emissions. There's an intriguing aspect to the cloud of estimates that you see here, and that is that people agree on the order of magnitude of the impact, a few percent of GDP, but they don't agree on the sign. Even here, there are a couple of estimates that say, well, this would actually be net beneficial still. The uncertainty about all this is rather large. This is roughly the 95% confidence interval. That's what the dotted lines denote. Obviously, that's sort of very narrow for very small changes, and then it sort of expands as you get into greater warming. It's also asymmetric. That is, the probability of the size of a positive surprise is much smaller than the size of an equiprobable negative surprise. Right? The confidence interval is asymmetric. The reason for that is actually manifold, and it sort of like goes through the structure of the entire problem. the best guess of the climate sensitivity, that is how much would the world warm if CO2 concentrations were to double, is 2.5 degrees. But then the uncertainty range about it is 1.5 to 4.5. So that is already asymmetric. Right? Standard deviation in one direction is 1, the standard deviation in the other direction is 2. It is easier to imagine that the Indians and the Chinese will burn a lot of coal, that is, that emissions are a lot higher, that all of a sudden they will switch to solar and wind. So in the emissions there is uncertainty and negative surprises are more likely. Most of the impact functions are nonlinear, that is, if warming doubles, then the impacts don't double but they quadruple or more. And somewhere nagging in the back of our minds are catastrophic scenarios about climate change. It's very hard to imagine, and nobody has ever claimed that if the world would get warmer, then all of a sudden world peace would break out and we would all be blissfully happy. That nobody's ever said that, and nobody, I don't think, ever had any ground to say. But the opposite people have said. And it's relatively easy to paint catastrophic scenarios of climate change. And one example would be, I didn't touch you, just walked past. One example would be Bangladesh, right? Low-lying, very densely populated. Sea level rise would be a massive problem in Bangladesh if they don't get their coastal defenses in order. Then 20, 30, 50, maybe 100 million people will have to migrate. Where to? Well, there's higher areas in Bangladesh as well. There's already a low-level civil war going on there. The people from the coastal plains and the people from the hills in Bangladesh really don't like each other that much. So if you take 50 million people from the coastal plains and put them in the hills, that would be mayhem. But chances are they won't stay in Bangladesh, they would spill over into India. India already has an immigration problem from Bangladesh. So you can imagine that could get nasty. Also, most Bangladeshis are Muslims, and they would sort of get into Hindu lands, and you can imagine that would go wrong. And if that sort of escalates into full-blown conflict, violent conflict, and you could imagine that the Pakistanis sort of get in and say, we're going to come to the rescue of our Muslim brethren, and that could mean nuclear war on the Indian subcontinent, right? You could sort of imagine a lot, I'm not saying that this is likely, but you could imagine a sequence of events of sea level rise leading to nuclear war. And that means that sort of the downside risks are much, much greater than the upside risks. And we should take them into account. We should also take into account that we're probably not going to stop at 2 or 3 degrees of warming. We're going to get beyond that, but beyond that, the impact studies get very, very rare, and there's a lot of speculation. Downside risk and speculation of what is going on here should make you very, very wary of treating into what really is a big unknown. And perhaps we should not say that climate change, that a century of climate change is equivalent in welfare terms to losing a year of economic growth, but perhaps we should be saying it's equivalent to losing a decade of economic growth, right? Once you start accounting for all these things. I've given you the caveats, still lots of missing numbers. For instance, the impacts of climate change on tourism are not included. There's an obvious and big impact. Definitely the enumerative studies don't look at the interaction between the impacts, some of which are quite substantial. For instance, there is a separate assessment of the impacts of climate change on agriculture. and the impacts of climate change on water resources. Those two things have been estimated separately, but agriculture uses 70% of the world's fresh water. You can't assess them separately, yet that is what people have done. The assumptions that we make about how people respond to climate change are terribly important, as I argued this morning, but very hard to model. And the models that we use are very stylized in the sense that people are either incredibly dumb, they don't respond at all, or they are incredibly clever. They sort of like see climate change coming 20 years down the road, and they can accurately forecast what the climate in 20 years would be and respond optimally to this. The low probability, high impact, nuclear war on the Indian subcontinent, that sort of thing are typically not being included, and indirect impacts on economic growth and all those things have been ignored. So this picture is far from the final one, but it is the best that we have. We're talking about the total impact of climate change. I also said that we're going to use this in a cost-benefit analysis. In the cost-benefit analysis, of course, we evaluate things at the margin. So I'm going to look a little bit at that in the remaining 15 minutes. So the way to think about this is that the marginal damage cost, often called the social cost of carbon, is the damage done if you emit an additional ton of CO2, or the benefit gained if you avoid emissions or reduce emissions by a ton. And technically, it is the net present value of the monetized impact normalized by a change in impact. So a change in emissions. So what you do is you have an impact model, say this curve here. Let's assume that this is time or something. This is what your impacts look over time for your best guess or your baseline scenario of emissions. Then you change emissions by a little bit, and you get therefore a slightly different curve, ever so slightly different. You take the difference between the two, you discount it back to today, and then normalize it by your change in emissions so that you get an approximation of that first partial derivative. Right? You may think that the social cost of carbon or the marginal damage cost is the PIGU tax. That's not entirely true. The PIGU tax is the marginal costs if the emissions are optimal. But it's actually a fairly close approximation of the PIGU tax. So it is also a normative concept in the sense that it tells us if we want to maximize welfare, this is the tax that we should apply to greenhouse gas emissions. And it is a normative concept in the sense that it reflects our values. For instance, we discount things back to today, so the interest rate at which we discount comes into play. And that is partly a normative concept. I'll get back to that in part 3. Also, we somehow valued things such as impacts on health, impacts on nature. That also is partly normative, right? So the numbers that I'm going to show are normative in two senses, in the sense that it tells us what to do in climate policy, but it also reflects how we look at the world. In the previous graph, there were 27 estimates of the total impact of climate change. On last count, there were 753 estimates of the social cost of carbon. And you may wonder, how can that be, right? Because the one is the marginal to the other, is the derivative of the other. So if you have 30 odd totals, you take the first partial derivative, you should end up with 30 derivatives, not with 750 derivatives, right? The reason for the difference in the numbers is not because we don't know how to take derivatives, but follows from the fact that there's actually additional degrees of freedom that are introduced. So there's 27 dots, right? And then different people have drawn different curves through these dots. So that is one degree of freedom that is introduced. Different people make different assumptions about what future emissions would be. It's another degree of freedom. Make different assumptions about how climate would respond to those emissions. Another set of degrees of freedoms, and so on and so forth. Right? So you can indeed go from 27 primary estimates to a large amount of marginals. If you have a large amount of estimates on something, you can do fancy statistics. And the thing that is done here is that a cumulative density function is drawn through this. And the CDF is just the integral of the PDF, right? The way to read this is as follows. If you consider all estimates, here in the black line, we look at the median. So what do we find is that there's a 50% chance that the Pigou tax should be smaller than $300 per ton of C, and a 50% chance that it should be greater than 300. And similarly, there is a 28% chance that it should be smaller than 0, that we should be giving a carbon tax. Which of course also implies that there's a 70% chance that it should be greater than 0, that is, we should be applying a tax. Rather than a subsidy. Now, if you have so many estimates, you can also do sample splits, and then perhaps we're going to learn a few things. So the sample split that is applied here is as to the discount rate that was used, and it's here given in the pure rate of time preference. I'll get back to what that means. It's essentially the utility discount rate. That means that the money discount rate is roughly 2.5% higher. So say this is for a 5% discount rate, this is for a 3% discount rate, and this is for a 2% discount rate. Right? What do you find? If you use a higher discount rate, you care less about the future, therefore you care less about climate change, and the social cost of carbon should be smaller. Right? What do we find? Let's focus on the median. For a 5% discount rate, the median is around 60. For a 3% discount rate, the median is around 160. And for a 2% discount rate, the median is around 475. So that is indeed what we find. Right? The lower the discount rate, the more we care about climate change, and therefore the higher the carbon tax that we would apply. The story doesn't end there. If you look at the 5% discount rate, then you see a fairly well-behaved CDF. So that is constrained between -25 and 175. It's sort of like compact, and that's it. It starts at 0 and it ends at 1, as a CDF should. If you use a lower discount rate, then yeah, it starts low and it goes high, but it doesn't quite start at 0 and it doesn't quite go to 1. Right? If you use a very low discount rate, then it doesn't even get much beyond the median. Right? For a carbon tax of $500. Again, this should be intuitive. The lower your discount rates, the further, the more you care about the future, and therefore the further you need to look into the future. Now, life is reasonably predictable over the next couple of weeks. We have a rough idea of where we will be in 20 years' time, 200 years' time. Basically clueless, right? So the further you look into the future, the larger the uncertainty becomes. But if you opt for a low discount rate, then you have to look far into the future. For a high discount rate, the far future doesn't matter, it's completely discounted away, and therefore the uncertainty about the far future is discounted away. Not so for a low discount rate. So it's not just that your median estimate shifts towards zero, but it's if you use a higher discount rate, but also the standard deviation becomes much, much smaller. Right? So here are some numbers, all in dollars per ton of C. The mean is about 600 for 2% discount rate, about 210 for 1%, 3% discount rate, and about 40 for a 5% discount rate. This is in dollars per ton of C. We may be used to thinking, maybe not, in terms of the price of emission permits, right, which the week before last I told you was around €5 per ton of CO2. The two are actually very close to each other. So the difference between C and CO2 is that you should divide this by 2.76. And then you should take into account the difference between the euro and the dollar, and then we actually get to a price of carbon that is fairly similar to the price of permit trade, of the traded permits, which is sheer coincidence. Here we're looking at the PDF of the same thing, it's perhaps a shape that you're more used to. All for a 5% discount rate, all studies in blue, and then in the studies in green, this thing is estimated along a no climate policy scenario, whereas in red, what people did was estimate this thing, the green thing, so this is what a carbon tax should be, impose the carbon tax, reran the model, and then sort of re-estimated this thing. It's slightly different because if you impose a carbon tax when emissions come down, you have slightly less of a carbon problem, slightly less of a climate problem, so you would expect a shift to the left. The problem becomes smaller, and actually will take away some of the tail. But at the same time, what you see is that the red and the green are very, very close together, right? So for the social cost of carbon without climate policy, we estimate this thing to be, what is this, 35, right? For the BQ tax, we say put it at 25. So it's close together and well within the margin of confidence. So, I'm actually almost on time. We talked about the impacts of climate change on welfare. The benefit of climate policy, we were talking about in part 3, is of course the impact, the negative impact that you avoid if you reduce emissions, right? I hope I've made it clear that these estimates are not the most solid in the world, and there's a lot of uncertainties and an enormous amount of assumptions that go into that. maybe sort of believe the state of the art, then climate change may not be the biggest problem of humankind, right? Not even the biggest environmental problem, perhaps. I've also made it clear, and I'll come back to that at length as well, that some of the assumptions that go in are objective, in the sense that the question is, or they're positive perhaps, in the sense of how much would sea level rise if the world were to warm by, right? That's a positive question, but there's also normative questions. Somebody falls ill, and how much value do we put on that? And the answers that are shown are a mix of that, and that also explains some of the controversies that are around these numbers. That it may simply be that people do not accept the valuations that we impose, that they do not accept the discount rates that we investigated, and so on and so forth. Right? So it's the positive parts of this story are just very uncertain. The normative parts of the story are very controversial. Right? That makes it a nice explosive mix. Okay, I'll see you guys next week.